Hello, we are project 21078 and our project name is Cost-Effective Helium Extraction from Natural Gas. Our mentor is Thomas Olden and we are not sponsored by a company, but we are sponsored by our department, which is Chemical and Environmental Engineering, and our team name is Helios.
Hi, my name is Dylan Cook.
My name is Emily Cosgriff.
My name is Joshua Fleetwood.
My name is Jessica Unwin.
This is our poster. You are welcome to pause the video and read through it, but we will cover the same information in this video. Most people don't think of helium as a rare resource, but it is in fact very precious and it's a non-renewable resource. It's used in a variety of different industrial and scientific applications. Examples of helium usages are in magnetic resonance imaging or MRI machines, gas leak detection systems, and in welding. The main source of helium is from natural gas. Some helium can be found in air, but it's currently too expensive to capture helium from air, so natural gas is the main and largest source. Although natural gas emits less harmful pollution when burned, purifying the natural gas requires a large power input. This power input usually comes from other fossil fuels. It requires such a large power input because we need to obtain pretty extreme conditions for a good separation. The objective of this project is to design a process for helium recovery from natural gas by using a double separation column cycle and cryogenic distillation technique. We want to process 50 million metric standard cubic feet per day of pipeline gas at 98% composition of methane stream, and we want to recover 96% of the helium and send that out at a composition of 65%. We also want to optimize our process in terms of cost and energy. To do this, we were adjusting the column pressure to minimize the power input across the distillation columns. We evaluated the use of turbo expanders versus Joule-Thomson valves. And we recovered energy from the system by utilizing throttling devices and heat exchangers.
Now we will go into the process design. After being extracted from the ground, the helium will go through two pre-treatment stages where impurities such as water, carbon dioxide, and sour gases will be removed. It's important to remove these before entering the nitrogen removal phase of the refinement process because they will freeze downstream in the high pressure and low temperature cryogenic operating conditions. The scope of work for the Helios project covers the nitrogen removal phase of the refinement process. This is sometimes referred to as a nitrogen removal unit. However, it is a system of multiple pieces of equipment.
There are two design alternatives that were evaluated in an attempt to recover the maximum amount of energy from the process. By removing the maximum amount of energy that we can from the system, we're able to also reduce the power input required and the cost of adding additional refrigeration loops to lower the temp of the feed. We compared a turbo expander gas turbine and a butterfly valve, which both throttle the gas, expanding it rapidly and quickly dropping the pressure of the feed. This is also known as the Joule-Thomson effect and was the primary means of removing heat from the system to get it to the cryogenic conditions required for separation. This is an overview of the equipment in our system. The process feed starts at stream 1, where it is fed then through a heat exchanger and turbo expander to remove as much of the heat and energy as possible before being fed into the double column cycle. In this cycle, the methane is liquefied into liquid natural gas product that can be shipped and sold, and the helium and nitrogen are removed, and the nitrogen is then liquefied to separate the helium. Liquefied nitrogen and liquefied natural gas are then fed back through the heat exchanger at the beginning of the process to remove heat from the feed to the system.
Now we will talk about the column optimization. The distillation column is the heart of our process. This column allows us to separate methane, nitrogen, and helium. Since it's the heart of our process, it comes with a high capital cost and operating cost. We optimize the columns by messing with the pressure in the columns to get the best operating cost. But first we started at high pressure and then we worked our way down to low pressure. So with this information, we determined that we would like to run our column at around 1,000 kilopascals to 1,500 kilopascals. This is the area where, on the chart to the left, you can see that it has lowest energy consumption by then making it lower operating costs. Next, we will talk about the Joule-Thomson effect in valves versus turbo expanders. Joule-Thomson is fundamental in cryogenic processes. It gives us the option to cool the streams without having to use external sources. As you can see on the table below, the main difference is the cost, size, and the energy gained from the turbo expander that does not happen in the butterfly valves. So now the question is, how did we determine between using a valve or a turbo expander? The first question we asked was, how does the pressure drop across the turbo expander and the butterfly valve compare? The turbo expander exceeded the butterfly valve in every single pressure drop we put it through. The next question was, how does the inlet temperature affect the Joule-Thomson effect over turbo expander and butterfly valve? The turbo expander had a larger delta T compared to the butterfly valve at every single inlet temperature until it reached about -80, and this is when the butterfly valve and the turbo expander became equal. From this information, we determined to use an inlet temperature at -70 to get the most effective range.
Now that we have concluded our project and gone over what makes our design effective and efficient, we have gained some key insights on what we could improve given an unlimited time and budget.
So some of the key recommendations that we can recommend are implementing the Linden cycle to optimize our helium extraction, because the helium cycle wasn't the most important process stream that we had to focus on. We didn't do really any optimization, so that is one area where we could become either more purified or even try to get a higher cost base from our separation. Another thing we can improve on is adding a tunable purity system for our helium stream. And so what we can do is, because of the fluctuation of prices for gases, helium could be something that we could create a more purified stream, and with that purified stream we could sell for a higher cost based on the market conditions, and with that we can help offset some of the potentially lower methane prices throughout the year, and again, all to reach our profitability, which is truly our end goal with our project. And lastly, we wanted to actually construct our system and see how viable our plant design was, because sure, we did the simulation and that's great and all, but it really would be great to put our ideas and theory to the test with an actual building.
Going over what we accomplished with our project, we were able to meet our design goal of 96% recovery helium and a purity of 65% in our exit stream with no more than 2% nitrogen in our methane gas line. We were able to utilize Joule-Thomson valves and turbo valves to lower operation costs by over 300%. We were also able to optimize our distillation process to reduce costs by 135% due to recapture and usage of operational energy. Finally, due to variability of natural gas prices, profitability can range from a net loss of $157,000 to a net gain of $39,000.